Welcome back. Having seen how to solve some numerical problems based on bending stresses in beams, it's now time for practice. 3 numericals shall be taken here and the video may be paused after every problem is covered. The solution obtained may be subsequently verified for correctness by resuming the video. Let's begin with practice problem 8. Find the maximum uniformly distributed load. The simply supported beam of T section as shown in the figure, which spans 6 meters, can support if the maximum permissible bending stress is not to exceed 200 megapascals. You may pause the video here, solve the problem and check for the correctness of your solution by resuming the video. The solution to practice problem 8 is provided here for reference and verification. The distance of the centroid of the given cross-section is first found out as 110.45 millimeters from the bottom edge and 39.55 millimeters from the top edge, rounded off to 2 decimal places. The area moment of inertia is calculated as 9.494 times 10 to the power of 6 in millimeter to the power of 4 units. For the uniformly distributed load, we invoke the formula for the maximum bending moment induced, namely W times L squared over 8. And after inserting in the flexure formula, we get the value of the uniformly distributed load as 3.82 kN per meter length. Here, it's worth to note that the value of Y as 39.55 millimeters is intentionally avoided since it may lead to a greater value of W kN per meter compared to 3.82 kN per meter, which when applied on the beam may cause induced bending tensile stress at bottom layers exceeding the permissible stress of 200 megapascals, which would be unsafe. Now let's continue with practice problem 9. A cantilever beam with 4 meter span carries a uniformly distributed load of 5 kN per meter and the permissible bending stress in the material of the beam is 15 megapascals. Design the section of the beam if depth to width ratio is 2. Again, you may pause the video here, solve the problem and check for the correctness of your solution by resuming the video. The solution to practice problem 9 is provided here for reference and verification. To design the section implies that the dimensions of the cross section need to be found out. The maximum bending moment in the cantilever beam is found to be W times L squared over 2, which is 40 kilonewton meter. The dimensions of the cross section are hence found out as width B is equal to 158.74 millimeters and depth D is equal to 317.48 millimeters. It's worth again to note that these sizes in decimals are normally not used in actual practice as beam cross-section dimensions. To take into account the standardization and interchangeability concepts, these are usually rounded up to the next available cross-section dimensions as per the available standards. Now, we continue with the final practice problem on bending stresses in beams. The problem statement is given as the tension flange of a cast iron I section beam is 240 mm wide and 50 mm deep. The compression flange is 100 mm wide and 20 mm deep, whereas the web is 300 mm by 30 mm. Find the load per meter run which can be carried over a 4 meter span by a simply supported beam if the maximum permissible stresses are 90 megapascals in compression and 24 megapascals in tension. You may again pause the video to solve the problem. Once ready, you may resume the video for checking the correctness of the solution. Welcome back. The beam with the loading is first schematically drawn with maximum bending moment as twice W kilonewton meter. The beam cross-section with the given dimensions is also drawn next. The centroid is found to be at 122.61 millimeters from the bottom and 247.39 millimeters from the top. The area moment of inertia is then calculated with a value 351.01 times 10 to the power of 6 in millimeter to the power of 4 units. Invoking the flexure formula for the top layer in compression as mentioned, W is found to be 63.85 kilonewton per meter, while for the bottom layer in tension, W is found to be 34.35 kilonewtons per meter. The lower value of the two is selected, that is 34.35 kilonewtons per meter, so that the stresses are within the permissible limits. In the next lecture, we shall understand the theory on flitched or composite beams in bending.